Hi everyone, welcome back. I'm going to do this next lesson in two parts. This is going to be all about earthquakes, and in this first part we're going to talk about what earthquakes are and how we measure them. And then in the second part I'm going to talk about earthquake impacts, how we forecast earthquakes, and then how we minimize the damage of earthquakes. So stick with me, we're going to go through these two different parts in different videos, but again, this first section is going to be about what earthquakes are and how we measure them. So first, let's talk about what an earthquake is. Earthquakes are essentially the rupture or the breaking and displacement of rocks. Earthquakes can occur on faults that already exist or on brand new faults. They can both generate earthquakes. Essentially, earthquakes occur when you've stressed a rock enough that it can't withstand that stress anymore and it needs to break or slip in order to release some of that stress buildup. Earthquakes take place on fault surfaces or fault planes. We usually think of faults as being planar features. They can also be curviplanar, but just for the sake of talking about faults, we're going to talk about them as though they are planar features. As illustrated in this image, you can see that this fault here is illustrated as a planar feature running through this block of rock. It's important to note that these faults they sometimes breach the surface of the earth and we can actually observe them, but a lot of times they are beneath the surface of the earth, or what we call a blind fault. Perhaps we can detect that there is seismicity below the surface, but we can't actually see the fault on which the seismicity is occurring. So although we will often look at maps that show fault traces on the map, we may not actually be able to see them at the surface. We just know that they're down in the subsurface. As I mentioned, earthquakes occur along fault surfaces or fault planes, and there are a few key locations that are important when we talk about earthquakes. So where the earthquake is actually generated, where that slip is actually occurring, we call that the focus or the hypocenter. You'll hear those two words used interchangeably. So that's the area here at depth along the fault plane itself where the earthquake is occurring. In the news, if an earthquake occurs, you'll probably hear newscasters talk about the epicenter. Where is the epicenter of the earthquake? We're always concerned about where the epicenter is. The epicenter is a location at the surface of the earth above where the earthquake actually occurred, or above the focus or the hypocenter. So that would be this location here that is at the surface of the earth above where the earthquake actually occurred. So it's important to know the difference between those two things, the focus or the hypocenter and the epicenter. Let's talk now about earthquake waves. Again, I kind of went over these when we were talking about earth materials and what the earth is composed of. But here I'm going to be talking about 4 different kinds of waves rather than just the body waves. I'll be talking about body waves as well as surface waves. There are 4 main types of waves that are generated from earthquakes. The first types of waves that are generated in an earthquake are the body waves, or the waves that sort of travel through the earth. These include primary waves or P waves, which are compressional waves, and S waves, which are the secondary waves, which are shear waves. So you can sort of see here in this illustration, compressional waves are if you were to take, for example, a slinky and sort of shove it, you would be creating compressional waves where the material is being compressed in some areas and then stretched and compressed. So that is a primary or P wave. A secondary wave or a shear wave is sort of if you were to take a rope and flick it up and down, you would notice that each of those waves has a wavelength, and it's sort of this wiggling motion along the rope. That sort of illustrates what a shear wave or an S wave is. These are both important when we're talking about earthquakes because P and S waves are the first waves to arrive at a seismometer location. So P waves will arrive first, followed by S waves with just a few seconds in between. So the next sort of category of waves are surface waves, and these are the really damaging wave types. These are the ones that occur on the surface of the earth, and they include what we call Rayleigh waves and Love waves. Rayleigh waves move particles in a circular motion. These are also called R waves sometimes. These look similar to S waves, but they're actually sort of a rotational motion. or a circular motion, and that can cause a lot of damage to buildings, to structures. Love waves, on the other hand, are lateral or horizontal motion, and so they're shifting the surface of the Earth side to side. And these really tend to develop in weak or unconsolidated materials at the surface, like sand or sediment. Places like the San Francisco Bay Area, which is made up in many places of unconsolidated sediment, the love waves could do some significant damage to places like these. You might remember from our previous discussion about plate tectonics that earthquake locations help us identify where plate boundaries are. Earthquakes don't happen everywhere. They happen in pretty specific locations, and they're most common at plate boundaries, although they do happen within plate interiors as well, and we'll talk about why that is. But at plate boundaries, you'll see lots of earthquake events occurring. If we zoom in on a mid-ocean ridge where we have a spreading center in the middle, as well as these transform zones in between, you might remember this from a previous lesson, you'll notice that we have a normal fault epicenter here. We'll get earthquakes occurring here at those spreading centers along normal faults typically. And then here at those transform boundaries, we'll also get transform fault epicenters. Keep in mind that volcanoes can also cause earthquakes and can cause seismometers to record earthquakes. So places like Hawaii, you'll see here there are some red dots there at Hawaii, illustrating that there are some shallow earthquakes occurring. In this map, you can see the difference between shallow earthquakes, intermediate and deep earthquakes, and you can see that we get a lot of shallow earthquakes here in the west coast of North America. There are many deep and intermediate earthquakes occurring in the regions around Japan, where we have multiple subduction zones. So you can kind of see the distribution of earthquakes here isn't equal everywhere. Next, let's talk about measuring earthquakes and sort of how we quantify them. The way that we measure earthquakes is using a device called a seismometer. In the past, we used mechanical seismometers where there's actually a spool of paper and a pen that would draw lines illustrating the motion of the seismometer, thus the motion of the earth during an earthquake, and it would record it on that rotating drum of paper. These mechanical seismometers came in two different types. We would have a vertical motion seismometer that would record the up and down motion of the Earth's surface, and then there was a horizontal seismometer that would record side-to-side motion of Earth's surface. Modern seismometers today use a magnetic weight, and they produce an electrical signal that is recorded digitally, and they're much, much more sensitive than the mechanical seismometers that we used to use. Let's talk a bit about how we locate the epicenter of an earthquake. So oftentimes you'll hear, again, newscasters saying, oh, there was an earthquake and the epicenter was in San Francisco, or the epicenter was, recently there was an earthquake in San Ramon, like this morning. How do we determine where the epicenter of an earthquake is? Well, we have seismometers all over the Earth now. We have lots of places where we can detect earthquakes, and this makes it really easy to locate the epicenter of these earthquakes. So remember I said that P waves, or the primary waves, they travel faster than the S waves. They arrive first at a seismometer location. The further away that a seismometer station is from the epicenter of the earthquake, the longer it takes for that earthquake to arrive, for those waves to arrive, and also the longer the time is between when the P wave arrives and when the S wave arrives. So those will diverge the further away that the seismometer is from the epicenter of the earthquake. So if you record S and P waves at multiple seismometer locations, you can actually draw up a curve that illustrates the distance between the epicenter and the seismometer against the travel time in minutes. So you can see that we have these two curves of the S waves and the P waves plotted. And that can help you identify how far each of those stations are from the epicenter of the earthquake. Using this plot, you can then calculate how far from each station the epicenter is, or how far the station is from the epicenter. That's a better way of putting it. then you can draw a circle on a map with the radius of the distance of the epicenter to your seismometer station. If you draw at least 3 of those circles, where those circles intersect, that shows you where the epicenter of that earthquake is or was. I want to talk about 2 terms that often get used interchangeably but actually mean something a little bit different. You'll hear people talk about earthquake intensity and earthquake magnitude. Those 2 terms actually mean something a little bit different. So intensity is the word that we use for what people feel during an earthquake or how much damage is done. Those 2 qualities sort of go into the calculation of what we call intensity. And we often report intensity on websites like usgs.gov. You can go on to their earthquake webpage and see recent earthquakes and what the intensity of those earthquakes was like. And then there's magnitude. Magnitude is an estimate of the energy that's released during an earthquake. So how much energy was built up when the fault was stressed and then released when the fault ruptured. What's interesting about these terms is that 2 earthquakes with the same magnitude can have different intensities. Intensity really relies on population density, what the material at the surface of the earth is made out of, which influences how much damage is done, how many buildings are in the area, how many structures there are. That can all really influence the number of the intensity value that we give an earthquake. Magnitude, on the other hand, is simply the release of energy. So again, 2 earthquakes with the same magnitude can have very different intensities depending on where those earthquakes are occurring. You've probably heard of the Richter scale. This is a pretty well-known or often referred to scale. It's also called the local scale. This was developed in 1935 by Charles Richter, and it's actually not the scale that we use anymore to talk about earthquakes. We use a new scale, which I'll talk about in just a moment, but we got to give the Richter scale some airtime because it's just so well known. The Richter scale measures local magnitude, so it doesn't really work for earthquakes that are more than 400 kilometers away from the seismic station. But it works well for local magnitudes, and it's based on the maximum amplitude of S waves on the seismograph. So when that earthquake hits and the seismograph records the S wave in particular, that S wave amplitude is what we use to give a Richter scale magnitude for the earthquake. And this is an estimate, again, of how much energy is being released during that fault rupture. The Richter scale or the local scale ranges from 2 up to 6, and you'll see in just a moment why we needed a new scale. And that has to do with the magnitude of earthquakes that our planet experiences. The Richter scale doesn't capture our largest earthquakes and doesn't actually express the energy release in a very meaningful way. So today we actually use what's called the moment magnitude scale, and that is denoted as M sub W frequently. And this magnitude is calculated using information about the rigidity or the strength of the rock that fractured, the surface area that ruptured on the fault, because the entire fault may not have ruptured. It could have just been a portion of the fault. So that surface area is part of the calculation, as well as the displacement. So how much the fault actually was displaced or how much it slipped. So some of the implications for this include that the stronger the rock material is, or the larger the area, or the more movement there is in an earthquake, will lead to a larger magnitude. So stronger rock material will lead to a larger magnitude earthquake, or a larger rupture area, or more movement. So these are all sort of considered in the calculation of the moment magnitude of an earthquake. The moment magnitude scale and the Richter scale are both logarithmic scales, which means that with each step of the scale, you're actually increasing the magnitude many times over. So from one step on the moment magnitude scale, from a 1 to a 2, you're actually increasing the release of energy 32 times. And the same goes from a 2 to a 3, you're increasing the energy release another 32 times. So the difference between a magnitude 1 and a magnitude 2 is actually quite a big difference. Now, I've talked about how we measure magnitude or energy release from an earthquake. Now I want to talk about how we measure intensity, or how much damage is done, or how people actually experience an earthquake. That's what we call intensity. We use a scale called the Modified Mercalli Intensity Scale, or the MMI. And this was invented by Giuseppe Mercalli in 1902, and it was then modified by some people, Harry Wood and Frank Newman, in 1931. And this Modified Mercalli Scale is used today, and it measures, again, the intensity of the quake. The Modified Mercalli Scale, again, measures intensity of an earthquake, which, again, is the damage done and how people actually felt or experienced it. And we use Roman numerals for the Modified Mercalli Scale to differentiate it from the original Mercalli Scale. Some factors that can affect the amount of damage or the intensity of an earthquake include its magnitude. So we consider the moment magnitude value when we're calculating its Mercalli scale intensity. We consider the distance from the epicenter. So the intensity is going to be different closer to the epicenter. It'll be higher closer to the epicenter, and less intense the further away you are from the epicenter of the earthquake. The depth of the earthquake influences the intensity as well as building design or structural design, and the material at the surface of the earth, whether it's lithified rock or whether it's unconsolidated sediment, can really affect the amount of damage that is done, and thus the intensity of an earthquake. You can see an example of the Modified Mercalli Intensity Scale on the left there, and you'll see, again, we use Roman numerals for this. And, you know, at a 1, it's detected only, the earthquake would only be detected by seismic instruments, not by people, and it doesn't cause any damage. At a 2, it's felt by maybe a few people who are standing still and can actually feel it. At the higher end of the Modified Mercalli Scale, there are notes that say, you know, masonry structures and wooden structures were destroyed. The ground was severely cracked in places. There were landslides. Maybe dams collapsed. And facades of buildings collapsed or were severely damaged, complete destruction of buildings. So this scale is really helpful for describing the intensity, or how we as humans really feel that earthquake and how we experience it. So in this video, I talked about what earthquakes are and how we measure them. In the next part of this lesson, I'm going to talk about earthquake impacts, how we forecast earthquakes, and how we minimize the damage from earthquakes. I'll see you there.